Statics. The study of forces on an object when there is no motion. Actually, it could also be when there's constant motion, constant velocity. But we'll just take the situations where there's no motion. Things are at rest. And we're going to concentrate on concurrent coplanar forces. And they don't have to be concurrent and coplanar, but that's what we're going to stick to. Concurrent means intersecting in one spot, one point. We're going to be looking at just single points. And coplanar means flat in a plane. Equilibrium is a state of balance when there's no acceleration. F net equals 0. So once again, we could have something that's at constant velocity, but we're just going to stick to the at-rest situation. So here we have a situation. It's a 350 Newton weight hanging by a string to a spot here. Let's call this spot point A. All these red lines are strings. And this black stuff is supposed to be a ceiling and a wall. This is the ceiling up here. And then a wall over on the side here. And those little hash marks just represent, above the ceiling and behind the wall. But these strings or ropes are holding this weight up. And the top string is at a 75-degree angle. But the point of concurrency here is point A. So I'm going to draw my free body diagram in regards to point A. If I start off like this, I have a rope pulling that way, I have a rope pulling that way, and a rope pulling this way. I'm going to call this T1, tension number 1, force number 1, T2, force number 2, and T3. And the idea here is to figure out the tension in these three strings or ropes. Now, T1 we already know is going to be 350 newtons. I'll get to that in a second again. But what you want to do here is always get your diagram into component form. In other words, T3 is also already good to go. T3 is to the right. We don't know how much that is. But we do know that T1 equals 350 newtons straight down. It's 350 newtons. That 3 there is hard to see. But T2 has two components. Alright, so I'm going to redraw T sub 2 and find the components. There's T sub 2. And we'll draw our components. There's T sub 2y and T sub 2x. And we can draw our rectangle. And we know from the trigonometry of the diagram above that this is 75 degrees down here in this corner. And if I just use my component equations, the cosine of 75 degrees equals the T sub 2x over T sub 2. In other words, T sub 2x equals T sub 2 times the cosine of 75. And likewise, if I go through the same process, T sub 2y is going to equal T sub 2 times the sine of 75 degrees. So those are important ideas there. I'm going to box those off. And what I'm going to do is complete my component diagram over here in the upper right. So I have my T sub 2y in the upward direction and my T sub 2x. Now once again, since this is at rest, F net is 0, what that means is that the upward T sub 2y must equal the downward T sub 1, so T sub 2y must be 350, just like T sub 1 is. And now we have from down here T sub 2y, which is now 350 newtons, equals T sub 2 times the sine of 75 degrees. We can solve for T sub 2. We get T sub 2 equals 362 newtons. Alright, it's one of our answers. And we already knew that T sub 1 was 350. So we have 2/3 of the problem done. And now, I'll switch to blue. Since I know what T sub 2 is, I can take this equation right here. I'm going to find t sub 2x, is going to be equal to t sub 2, which we know is 362, times the cosine of 75. That gives me t sub 2x equal to 94 newtons. All right, but also looking at my free body diagram up here, I know once again that F net left and right is 0, so the t sub 2x must equal t sub 3. Therefore, t sub 3 equals 94 newtons. Statics problem number 2. In the olden days, we used to dry our clothes outside. We had clotheslines. Here we have a clothesline hung between two trees, 20 feet apart. It's a rope. And a young man by the name of Eric is going to grab point A, which is the midpoint, 10 feet from either tree, and pull down, and the rope will deflect, kind of like in the lab, the clothesline lab we did when we hung a weight between two spring scales. So point A is the point of concurrency here, the point of interest. And we're basically going to have the rope now acting like two ropes, and we're going to have Eric pulling down right there with his full force, 185 pounds. And we're not going to do any conversions here, and I'll show you why as we go along. But he's hanging off the ground. He's not standing on the ground anymore. He's hanging by his hands, by the way, pulling down, suspended, and making the rope really tight. Now, once again, I'm going to call this T1 and T2 for the tightness in those two pieces of rope. But since there's symmetry here, T1 will equal T2 because point A is the midpoint. If A was not the midpoint, then we would not have symmetry and T1 would not equal T2. But like the last problem we just did, we need to break this problem, the angled forces, T1 and T2, into their components. Once again, point A is the important spot, and the 185 is a good number to use. We have to use it. It's easy to use. It's straight down. But T2 is going to have two components. There's going to be T2x and T2y because it's pulling to the right and up. And T1 is pulling to the left. There's going to be a T1x. And this gets a little bit tricky. You could actually put them on top of each other, but I'm going to separate them a little bit. T1y. Everything's So we have all these components now acting on point A. And because of symmetry, we once again know that T1y and T2y are equal to each other, and they have to sum up to 185. Therefore, T1y must equal half of the 185, which is 92.5 pounds. You could round it up to 93 if you wish. Now, if I redraw T1 or T2, but I'm just going to focus on T1 for now. T1 is up and to the left. And if I finish off my vector diagram, in fact, what I'm going to do is I'm just going to draw it a little bit different this time. There's T1x and then T1y, like that. And I can make it a full rectangle, but this is good enough for now. The problem is, all I know right now is T1y is 92.5. I cannot solve that triangle because I don't know the angles. However, if we go back over to the tree diagram, let's take a closer look at the clothesline. So the clothesline, before Eric grabbed it, was horizontal. When he grabbed it, the point A, which is in the middle, sags to a lower spot and this clothesline stretches, but it stretches to something like this shape. All right, and there's a little sag in here, and I'm going to make this blue. This little sag straight up and down is 9 inches, that little blue segment right there, and that would be a right angle. That splits that big triangle into two small triangles, but let me just highlight this triangle right here, where this little leg over here is 9 inches. That's the symbol for inches. And this top piece is 10 feet, but 10 feet is 120 inches. 120 inches. That would be the distance from there to there, half of the 20 feet. So we're looking at this blue triangle right now. And I don't care about the hypotenuse, so I could figure that out. But what I care about is this little bitty angle right there. That little bitty angle right there. And let's just call that theta. So the sine of theta, actually the tangent of theta is going to be 9 over 120, because that's why I put both of those measurements in inches so I could compare them and figure out the angle. The angle comes out to be, inverse tangent, comes out to be 4.3 degrees. All right, that's important because what that does is that carries over into our vector diagram for the forces. This triangle that I drew, the red triangle, is sort of upside down, but by trigonometry and alternate interior angles, you could prove that this angle right here, this little thin angle, also is the same as the angle in the deflection diagram on the left. That theta right there is 4.3 degrees. If you want to see a proof of that, come and see me. Otherwise, think about it for a little bit and work through that yourself. But that's 4.3 degrees. Okay, so now if we know that that's 4.3 degrees, and we know T1y is the 92.5, and I want to find T1, I can just use the sine of theta, which is 4.3, equals T1y, which is 92.5, divided by T1. So T1 comes out to be 1,200 pounds. And pounds are a force, legitimate force. We don't have to use newtons. But that's T1. That's also T2, or basically the tension in the clothesline when Eric grabs the clothesline.